AI is just moving at this dizzying pace, right? Every week, it seems like there's a new model that just shatters all the old records. But what you don't always see behind this curtain of amazing software progress is this brutal, physical battle being fought against the laws of physics. So let's dive into that hidden war. It's such a frustrating cycle, isn't it? I mean, one second we're celebrating some huge leap forward in what AI can do, and the very next we're hearing about a global shortage of some tiny little component we didn't even know existed. It feels like we just keep smacking into a new wall over and over again. And really, that's the absolute perfect way to think about it. The engineers who are building the future of AI, they're basically playing the most expensive, highest stakes game of whack-a-mole you could ever imagine. Because the second they smash one hardware problem, boom, another one pops up, and it's usually even harder to solve. Okay, so the very first mole to pop its head up, pure raw computation. The early AI models, man, they were slow. And that's because the chips we were using just weren't designed for the kind of math that AI needs. This was the first big wall that had to get knocked down. And this slide just lays out the solution perfectly. So think of a CPU, right? It's like one super smart person with a calculator, solving really tough problems, but one at a time. But see, AI training isn't one big, complex problem. It's millions, even billions of super simple problems that all need to get solved at the exact same time. And that's where the GPU comes in. It's not one smart person. It's like an army of thousands of workers, all doing a tiny piece of the puzzle at once. It's all about parallel power. And the impact? It was absolutely transformative. All of a sudden, training a model that used to take days, now it could be done in just a few hours. And NVIDIA, with their CUDA software, they basically cornered the whole market. They became the engine of this whole AI revolution. So just like that, whack, the computation wall was gone. Problem solved. Or so we thought. You know what happened next. So with our processors now flying at lightning speed, of course, a new problem popped right up. It's kind of like having a Formula One engine, but you're trying to feed it gas through a tiny little straw. The GPU was just starving for data because the memory couldn't get it there fast enough, and this became known as the memory wall. So how do you fix that? Well, this slide shows the solution perfectly. It's called high bandwidth memory, or HBM for short. If your regular memory is like a bumper-to-bumper single-lane road, HBM is like a massive 8-story superhighway. They literally stack the memory chips on top of each other, which opens up this absolute fire hose of data that can flow straight to the GPU. And hey, don't just take my word for how important this is. NVIDIA itself says that memory bandwidth, that's just how fast you can shovel data onto the chip, is responsible for a mind-blowing 80% of an AI chip's total performance. It's everything. Okay, so we built the highway. Mole whacked, game over, right? Not so fast. Because in solving one problem, we immediately created the next one. See, building this HBM highway is incredibly difficult, and demand just went through the roof, basically overnight. The result, a massive, crippling global shortage. And you can see the problem crystal clear right here. The entire planet's supply of this absolutely essential tech, it's controlled by just 3 companies. That's not really a market, that's an oligopoly. And it's all concentrated in just a couple of places, which makes the whole AI supply chain super, super fragile. So what happens when you have that kind of setup? A classic supply and demand nightmare. Prices for HBM are expected to literally double. Right now, AI companies are in this crazy bidding war. They're even paying huge deposits way in advance just to get a spot in the production line. So, of course, the industry's already thinking about its next moves, trying to get ahead of this thing. You've got ideas like PIM, which is basically putting a little mini calculator right inside the memory itself to do some work before the data even moves. Or CXL, which is a wild idea to link the memory of a bunch of different computers together into one giant pool. These are all just desperate attempts to whack the next memory mole before it even has a chance to pop up. All right, so let's recap. You've got your super-fast GPU engine. You've got your ultra-wide HBM highway for fuel. You think you're good to go, right? Nope, not even close. A brand new mole pops up, the great assembly problem. You have to actually connect all these amazing parts together. And this is not like snapping Legos together. We are talking about one of the most delicate, precise manufacturing jobs on the entire planet. And this analogy just nails it. You have the engine, the GPU. You have the fuel tank, the HBM. But the one special factory that knows how to put the car together is completely booked. There's a huge line out the door. That whole assembly process, it's called advanced packaging. And here is the source of that traffic jam. One single company, TSMC, controls something like 90% of the world's capacity for this advanced packaging. They do it with their CoWoS technology. That's chip on wafer on substrate. And it's the secret sauce that bonds it all together. But what it also does is create an absolutely unbelievable single point of failure for the entire AI industry. And the fallout from this is huge. I mean, NVIDIA alone books up more than half of TSMC's entire capacity. That causes massive delays for everybody else. We're talking AMD, Google, you name it. The whole supply chain just slows to a crawl, with everyone waiting in line for their turn at this one critical factory. The good news is it's expected to get better, but not until the second half of 2026. So we have a while to wait.
Okay, now we get to what might just be the final boss in this whole game. This is the mole that we can't just fix with some clever new chip design. Let's talk about power. We're talking sheer raw electricity.
I want you to just take a second and really let this number sink in. 10%. By 2026, so just a couple of years from now, AI data centers could be guzzling up 10% of all the electricity consumed in the entire United States. To give you some perspective, a single big AI data center can use as much power as a small city. This is the power wall, and we are flying straight towards it. And of course, this brings us right back to our car analogy. We've engineered the engine, we've built the fuel highway, we've found the factory to assemble it. We have built the ultimate hypercar. But what good is that car if there just aren't enough charging stations in the whole country to actually run it?
Now, you might be thinking, okay, surely that has to be the end of it. But no, this game, it just never stops. The people in this industry are already looking years down the road, trying to predict which moles are going to pop up next. So let's take a look at this timeline for a sneak peek. Pretty soon, the bottleneck is going to be the interconnects. We're talking about the actual physical roads between the chips. Yeah, you have the superhighways, but if the on-ramps are all clogged, you're still stuck. After that, we might literally hit the laws of physics. We just can't shrink transistors any smaller. And way out on the horizon, we could face a data wall. That's the point where we actually run out of high-quality human data on the internet to keep training these things.
And really, this is the main thing to understand. The race to build bigger, better AI isn't just a software problem. It's not just about writing cleverer code. It is a relentless, brutal physical chase. Every time we come up with some brilliant solution or have a new engineering breakthrough, all it does is reveal the next wall that we have to climb. And that next wall is always higher. So it all boils down to this one huge final question. We're basically in an arms race against the laws of physics. On one side, you've got human ingenuity, constantly dreaming up these incredible ways to get around these physical walls. And on the other side, you have AI's seemingly bottomless hunger for more computing, more memory, more data, and more power. So who's going to win?